Hi, I am Jacob Tooby, and in this video I will present my graduate research accomplished while obtaining my master's degree. It contains pictures and short video clips that will express the breadth of knowledge and detail in the research. I highly recommend you log on to my website at jacobtooby.com to view even more past engineering projects and a list of my references as well. I graduated from the University of California in San Diego with a bachelor's and master's degree in mechanical engineering. My graduate research and thesis focused on my passion, which is control systems theory. I currently work for Hawker Pacific Aerospace, which is a maintenance, repair, and overhaul facility for airplane landing gear, and manage the Douglas program. I have a passion for engineering, problem solving, and innovation. I've displayed these and more character traits throughout my university and professional career. As the list shows, I've learned and enjoy using my eclectic set of software skills to solve technical challenges. While working towards my master's degree, I performed research at the University of California in San Diego and wrote a thesis entitled Control and Optimization of Wave-Induced Motion of Ramp Interconnected Craft for Cargo Transfer. I conducted my research at the Cymer Center for Control Systems and Dynamics at UCSD, and it was sponsored through a grant by the Office of Naval Research. In the forthcoming slides, I will explain the system models used and the three control theory applications investigated. First is passive control. It consists of applying absorbers to each joint between the ramp and vessel. Second is extremum seeking. It can be thought of as a passive tuning method where key parameters are optimized so that a desired system response variable will seek to a maximum or minimum neighborhood value. Third is an active control method, where a controlled gyroscope is simulated on the T-craft to reduce its roll motion. My ultimate goal was to determine the sensing and actuation requirements to devise control and real-time optimization algorithms to stabilize the T-craft's roll, pitch, and heave degree of freedoms. This will ensure safe cargo transfer from the sea base to the amphibious T-craft. Due to the complexity and nonlinear nature of the dynamic model, the system was initially modeled with half cylinders for the vessels and a rectangular solid for the ramp. Once the mass and geometrical properties of the system is input into the SimMechanics model, which is a toolbox within MATLAB, the necessary analysis can be performed. Typical environmental disturbances that would affect the system at sea include waves, ocean current, and wind. However, in the forthcoming simulations, I have neglected the effects from current and wind and consider the ocean waves as linear planar waves and affect the system as would a spring and damper connection to the ground. The ocean waves were modeled using the Pearson-Moskowitz spectrum at sea state 3 and 4, which correspond to a significant wave height between 0.5 and 2.5 meters. This spectrum is a distribution of the wave energy versus angular frequency for a given sea state. As shown, the larger the wave height, the more the energy of the modal frequency wave is shifted to a lower frequency range. The sea elevation profile produced from the Pearson-Moskowitz spectrum when marched in space and time looks as follows. It is assumed the ocean waves disturb the system at all angles shown, with the blue lines corresponding to the phase shift at each point relative to one another, and the wave forces impact the system at the vessel corners as shown. Until now, I've talked about the various models for the static system and environmental disturbance. Now I will shift my focus to the dynamic modeling of the system and control theory applications. Before I begin to present the control applications and results, I'd like to briefly present the system's equations of motion derivation to convey their innate complexity. I use the modified Lagrangian mechanics approach to derive the equations, which account for dissipative forces as a function of velocity due to the damping effect. In short, the total kinetic and potential energy terms comprise Lagrangian L. Then, the total dissipative forces and moment terms, d, and the applied external force and moment terms, capital Q, were derived and plugged into the Lagrangian partial differential equation. To conclude the derivation, I then differentiated the equation with respect to each generalized coordinate and simplified. Due to the complexity as seen with the second order, nonlinear, and implicit terms, these equations could not be solved analytically. Rather, they were solved computationally through MATLAB's built-in numeric solver. Notice the inherent oscillatory nature for all 16 states in both the position and velocity solution graphs. This behavior is influenced by the ocean wave motion that continually disturbs the system in a spring damper-like behavior. I was able to passively control the system's response and produce meaningful results by applying a spring damper block between the joints in the SimMechanics model. As shown, the max angle with no passive control is plus or minus 10 degrees, while with passive control is plus or minus 0.1 degree. The following video clip shows that the resulting motion is relatively stable. The next control method implemented on our system is called extremum seeking, whose block diagram looks as shown. This can be used on a variety of systems provided that there is a local min or max neighborhood of system response values. If the system has no innate concavity, a penalty function can be introduced into the block diagram to bypass this issue and allow for the algorithm to function properly. The resulting signal J is known as a cost, which maps out any desired system-generated value for any given range of input values, which in this case is the ramp length R. The signal J is then passed through a washout filter, demodulated by a sinusoidal signal, integrated, multiplied by a gain, and passed through a second-order low-pass filter to produce a modified ramp length value R hat, which causes the system response to get closer to the desired extremum. Over time, the R hat value seeks to its optimal value corresponding to the minimum system response achievable for a given input. The cost map, or signal J, has an obvious optimal ramp length around 12 meters and a wavefront heading angle of about 30 degrees. Independent of their initial values, the extremum seeking algorithm will tune the ramp length and heading angle to their optimal values, as the following graphs and videos show. The final control method implemented is an active control method using a control moment gyroscope. The main point of gyroscopic theory is the precession phenomenon, which I will explain with an example. The ultimate goal is to reduce the T-craft's roll or oscillatory motion about the x-axis. The main part of a gyroscope is its flywheel, which constantly spins about the z-axis. When the vessel rolls due to an ocean wave, a precession motion occurs about the y-axis. A sensor usually triggers the actuators or hydraulic braking system to counteract the precession with an equal and opposite moment. Now this produces yet another moment in the opposite direction of the input roll to potentially eliminate the vessel's roll and promote a higher degree of stability. The equations of motion used for this simulation solely account for the degrees of freedom relevant to the T-craft and gyroscope system. As shown, comparing the system's behavior when the control moment gyroscope is off to the response when the control moment gyroscope is on, we see a major improved stability in the T-craft's rolling motion. The gyroscope control application is a great example that requires redesigning the cost map if one plans to integrate it with extreme seeking. The logical parameters to optimize are the flywheel's moment of inertia and spin velocity, while the variable to reduce is the vessel's roll. Naturally, the greater these parameters are, the lower the roll value becomes. Practically, these values cannot grow indefinitely due to the obvious constraints, and therefore a penalty function is introduced to provide the desired concavity in the cost as shown on the right. This concludes the graduate research summary during my graduate year at UC San Diego. The list shows the literary references that facilitated my research. These are some of the professors and mentors that I was fortunate to have worked with and who can vouch for my personal growth and commitment to excellence while working under their guidance. Thank you very much for watching. To view more of my past and current work, I highly recommend viewing my site at jacobtooby.com.